So today we'll be talking about performance of scientific applications on the new Comet HPC machine utilizing MVAPICH. So let's welcome Mahidhar.
Thanks. Good. Thanks, DK. So yeah, I'll go over some of the application performance on Comet, and you'll see we use pretty much all flavors of MVAPICH on Comet. The machine itself has a lot of pieces, basically proposed through UCSD, SDSC at Indiana. There's a virtualization component that Indiana is part of. It's basically Intel Haswell processors on all the nodes. We have a few nodes with NVIDIA K-80s, and it's a Mellanox FDR interconnect, and funded by NSF, of course. That's the machine itself. That's one row of racks. There's another one right behind it. Pretty compact. So in terms of system characteristics, it's about 2 petaflops total. It's a Dell integrated machine, as I mentioned, Intel Haswell processors with AVX2 and Mellanox FDR. About 1944 standard compute nodes. Each of them is a dual CPU with 12 cores each, so 24 cores total. 128 gigabytes of RAM. We also have 2 Intel SSDs in each of the machines, each of the nodes. So we usually have this in a RAID 0 configuration. So the users see about 240 gigabytes after we take away all the system stuff that we put on the same drives. So it's a nice local scratch that's worked pretty well on Gordon, so we kind of continued that in Comet. On the 36 GPU nodes, the processors are basically identical to the standard nodes. We have 2 NVIDIA K-80 cards on each node, with basically 2 GPUs each, so that's 4 GPUs on each node. We just got these large memory nodes, so that June has turned into August, but it should be in production pretty soon. So we have 4 large memory nodes with 1.5 terabytes of RAM each. And I think that's 64 processors per node. I mean, 64 cores per node. Another big system characteristic is that we're going to be making available high-performance virtualization, essentially allowing groups to do clusters within Comet with their own environment. And we're leveraging SR-IOV for that piece of it. And I have some numbers for that aspect today, which will probably get better because MVAPICH2 is probably a little faster than what we used on there. It's a hybrid factory topology. The system itself was aimed at the small to medium-sized user base. What we noticed is, looking at the Exceed user base and the job histories, you could cover almost 90% of the users, or actually even more, like I think 95% of the users with 2,000 cores or less. And the system itself is aimed at that kind of user base. So in terms of the topology, we have rack level 72 nodes with full bisection bandwidth, full connectivity there at 72 nodes, and then 4:1 over subscription cross rack. So it does make a big difference for some cores if you go off rack. Storage-wise, the vendor was Aeon, which is a local San Diego vendor, with 7.6 petabytes of storage. It's split over 2 cluster file systems. The net performance is 200 gigabytes per second. One thing that Comet is new with is we deployed ZFS on the back end of cluster, and also it has DNE, so the multiple metadata servers being active. And what's the project storage now on Gordon is going to turn into durable storage in the long term. and we actually allocate the project storage on our machine, so that piece is going to be automatically backed up to this durable storage piece. And that's still ongoing. We are in the process of setting that up. And standard home directory storage. We have a few nodes that let you host gateways and things like that, so that you could get access to the file system and the machine with very low latency. So they're on the same fabric. We'll end up having a virtual image repository when the virtualization piece comes in to play, and there's 100 gig connectivity going out from the center. That's the IB diagram. I think there's been a change in this a little bit, but for the most part, I want to focus on the 72 nodes at the rack level. So you end up with essentially 7 switches for the connectivity there, and then they go to the matrix, which is 18 links from each rack. So there's the 4:1 over subscription there to the matrix, which is with again IB, FDR IB. And our cluster is accessible through 40 gigabit Ethernet on the back end. So we have a bridge device that lets you go from the IB network to the Ethernet network. And the reason for this was we are actually looking into sharing the cluster file system over some places in campus, and also when the virtualization piece comes, there may be a segment of it that might show up there. So this gives us the flexibility to do those sort of things. I just want to go over Gordon a little bit because I'm comparing some of the results to Gordon today. So Gordon itself has been in production since February of 2012. Essentially 1024 standard bridge nodes. You have 2 sockets per node, and that works out to 16,000 plus processors, cores on the machine. It was the first machine to feature flash at a large scale. So yes, about 300 terabytes of Intel flash. On Gordon, this flash was actually in 64 I/O nodes, and then made available on each of the compute nodes using HPC or RDMA. And then that actually gave us a little flexibility on how we deployed the flash. Like there's some nodes with a lot of flash, and some nodes with 300 gigabytes of flash, and allowed us to test a lot of things. It does have a 3D torus interconnect, and actually a dual 3D torus. And I have a picture on the next slide. So it's a 3D torus of switches. So each yellow box there is essentially one switch which has 16 nodes on it, and 3 connections in each direction of the torus. So 18 connections going out. And we have the I/O node that's local to that switch on the same fabric essentially. So what that does is gives you an island which has 256 cores with full connectivity, and then over subscription. Again, like on Comet, Gordon is also oversubscribed going between those switches. The luster on this actually is routed through the I/O node that's local to each switch. So in terms of luster bandwidth, you don't have the bottleneck because it's actually going to go out through the nearest I/O node. So as I mentioned, I think we might be the only machine which will do this. We'll have all flavors of MVAPICH on it. So the default MVAPICH on Comet is MVAPICH2 version 2.1. I just saw the release 2.2a of MVAPICH2X, and I got that installed, so that's available now. This is to provide the MPI and PGAS programming approach. We have MVAPICH2 GDR, the 2.1 that was originally on, and the newest version that got released recently on the GPU nodes. And we're working on the virtualization aspect, and we're going to end up with MVAPICH2 to leverage the SR-IOV piece. In addition to all the MVAPICH stuff, we also have RDMA Hadoop from Dr. Ponda's HIVD lab on the system. And that leverages the SSDs and the cluster file system that's available on the system, in addition to the IDE. So going on to benchmarks, with MVAPICH2 we did a set of standard benchmarks, and this kind of represents a bulk of our user base using NPI on Comet. So Neuron is a simulation environment for modeling neurons and networks of neurons. This particular benchmark was modeling the olfactory bulb with 10,500 cells for 40,000 time steps. This is actually exposed through the neuroscience gateway that Amit's group leads, and basically available through the gateway to a lot of users. OpenFOAM, which is an open source software for CFD. We have a benchmark using LES for flow over a backward facing step. This is with 8 million mesh points and 200 steps at varying core counts. Quantum Espresso, which is an open source electronic structure calculations and materials modeling code base. The benchmark here was the gold surface with 586 atoms and 2,500 electrons for 5 iterations. It's a standard AUSO benchmark. There's a RAXML benchmark, which is a phylogenetics analysis tool. This again is used heavily by Cypress, which is one of the gateways that's available on Comet. Basically, I think this is almost 6,000 to 7,000 users are represented by that one application. It doesn't scale that much, but at the scale that it runs, it's done very well within MVAPICH. So going on to results, so you'll see like 3 sets in most of my results with the MVAPICH2. Some of these codes, when we originally installed them on Gordon, would only compile with OpenMPI. Not MVAPICH's fault. There was configuration issues and things that we worked out with developers. And, so originally we had these times with OpenMPI on Gordon, switched over to MVAPICH, which actually surprisingly in some cases gave like a immediate benefit of significant proportions. Like, I mean, at low core counts, that was pretty surprising. I'm sure if I go back and install the new version of OpenMPI, things will get a little better. But even with MVAPICH actually going between versions, you could see improvement. And then comparing that with Comet, which is running MVAPICH2 2.1. So the Gordon MVAPICH2 is version 1.9. So there's a little difference there. In terms of the cores, one thing to note is on Gordon it's 2.6 GHz scientific cores, and on Comet it's 2.5 GHz Haswell cores. So there's a little bit of a difference there in terms of the clock speed. In general, what we've seen is the performance is between 20 to 40% better on Comet with the Haswell cores. So on for Neuron, you can see it scales reasonably well, going out from 48 to 68 cores. I think most people run at the smaller core count, but there are a few cases where they need the memory to get to the high core counts. So OpenFOAM again was something that we switched from OpenMPI to MVAPICH2 and then used the same version on Comet. This is a benchmark using 8 million, again strong scaling, so 8 million mesh points with 200 time steps. You can see it scales pretty well, going from 96 to 384 cores, and actually it goes further if you keep scaling. Yes?
Is the same version of the MVAPICH2 on the 2 machines?
No, so it's 1.9 on Gordon and 2.1 on Comet. And I think the OpenMPI is also an older version on Gordon, because we kind of did the set, and then when Comet came and repeated everything with the newest setup essentially. So the only difference is some of these codes are kind of hardwired for NPI locations being in certain places, and the config files are not really like, it's not a configure make kind of thing. There's buried information in lots of files. So it takes a while to get them working with MVAPICH2. But it turned out it's worth the effort because it's a lot faster. So the quantum espresso, same story, strong scaling going from 96 to 768 cores. Again, quite a big improvement going to MVAPICH2, and Comet is quite a bit faster also. Now on this one, we'll go back to this benchmark when we go to the virtualization side, and you'll see the impact of some of the things. RAXML, as I mentioned, is a much smaller benchmark. It goes up to 48 cores. Typically, we're running with 2 nodes and Comet. That's the typical run size. You can see the scaling is kind of dropping off even getting to 48 cores. And if you go further out, it's not going to work out too much. But this is a heavily used code, and we're glad to see that work very well. And this is a hybrid MBI implementation. So those are pretty standard benchmarks, which is more of a sanity check to see if everything is working well with the system, and they're heavily used codes. So we're glad to see with MVAPICH out of the box, pretty much we got the performance we wanted. So the MVAPICH2X, I just installed this like a couple of days ago. So I have some preliminary benchmark results, essentially OpenFOAM put and get tests. So you got pretty good put latency, 1.42 microseconds, and get latency of 1.76. It seems a little faster than what you have on the website, I think, for the Ivy Bridge nodes. So doing pretty well. It's again out of the box, no pain. Everything worked out okay. OSU Atomics benchmark, same story, doing pretty good, I think, in terms of operation and latency. So I want to go on to the GPU nodes. So the MVAPICH2 GDR is set up on our GPU nodes, so using GPU direct RDMA. It's available through a straight up module load MVAPICH2 GDR. The features are all there. Just a quick note on the GPU architecture: the 2 GPUs are on different sockets on the PCI. So you have basically GPU 0 and 1 with CPU 0, and another set of GPUs on the other CPU, and which makes it interesting with some of the peer-to-peer stuff. But in terms of MVAPICH2 GDR, again, worked pretty much out of the box. We had some issues which were not MVAPICH related. It was actually the GDR copy library set up, but after that was sorted out, we got about 2.8 microseconds on the latency. I think this got a little bit better with the newer versions. That's the old 2.1 result. So the application I used in this one was HOOMD-blue. I think it's been talked about 2 times on out here already. It's a general focus particle simulation toolkit. What I used was the Leonard Jones liquid benchmark with 64,000 and equals 64,000. That's the references. So I did a couple of things. One was to look at using all the GPUs on one node, and then using 1 GPU per node, so that will go, everything goes over the network in that case. And pretty nice results actually. Even with 1 GPU per node, the performance is between 2 or 3%, within 2 or 3% of using all the GPUs on the same node. I haven't had time to tune this either. It's just preliminary stuff that I was testing with. I think this might get a little bit better with some tuning. So in terms of relative numbers, I think this is about 10 or 15% faster than what I saw on the website for HOOMD-blue for with the K40s. So it's not too bad in terms of performance, and it was pretty painless to build and use MVAPICH2 GDR, so I was happy about that piece. And again, this is preliminary and probably work with James to push this a little bit more. Yeah. Just wanted to put a slide in about Hadoop-RDMA. Basically, this is setting up HDFS, MapReduce, and RPC over native InfiniBand and RDMA over converged Ethernet. This is based on Apache Hadoop. This works with the Slurm scheduler. It's available on Comet in that location, and there's some nice benchmark results on DK website. So the last piece I want to talk about is the single root I/O virtualization. So the main motivation was we're trying to enable virtualization for groups that kind of want control over their stack. We've seen this question quite a few times where people say, oh, I need this, and this installed, and we go look at it and say, well, this is going to break this on the system, this is going to break this on the system, so we can't do it, and we have to turn them away. And usually, in the past, when you did virtualization, the performance hit was pretty much unacceptable. And you'll see, like if you go, say you pick up a Amazon EC2 VM, even with SR-IOV, with the 10 gig, the latencies are pretty poor. I mean, you get up to close to 60, 70 microseconds, and then almost, I think bandwidth is like 500 megabytes per second. So there's a huge performance hit doing that. So our approach was to use SR-IOV and try to see if we can mitigate some of the latency and bandwidth over it. And the way it works is to bypass some of the hypervisor functionality. So on Comet, and this is with MVAPICH, the default MVAPICH. We didn't actually test this with MVAPICH Word yet. So I think this is going to get a little bit better. But if you look at the bandwidth, at the large message sizes, basically it's line rate. In fact, we had a few tests where the virtualized number was a little faster than the real one. It's in the noise, but basically it's almost line rate on the virtualized bandwidth. And on latency, the hit was about 30%, but I think with the Word it's a little better. It's about 20%, right? At least I think the first number that I tried, I got something similar like that. So it's actually pretty good from a latency and bandwidth point of view. So we went and tried out a few applications. So the first one is a standard weather benchmark, WRF. It's a 12 kilometer resolution one. Originally we ran this with 96 cores when we were doing the proposal for Comet. We ran this on a SR-IOV cluster with, I think, assigned bridge nodes, very similar to the Gordon nodes. So we were comparing with the Gordon tests also. I now have Comet results for the same thing. So we were basically comparing the SR-IOV test cluster to an Amazon instance which had a faster clock with the same processors, or like slightly different processor, but basically sandwich. And for WRF, with it's a fairly benign communication pattern, so it's not too bad in terms of network dependency, at least for this size of the benchmark. So the hit when we did using the old cluster, which is with the standard bridge nodes, was about 15%. And on Amazon, if you did the same benchmark with 96 cores, you got a 44% slowdown compared to native performance. So it's pretty reasonable even at 15%, but with Comet, with the newest setup, it's down to 2%, like the performance difference at 96 cores. So I think that's really nice, and should give us some flexibility, at least to try out different stacks and give the user some control. Quantum espresso is even more dramatic because it pushes the network a bit. So you end up with, I think the EC2 essentially was 5x slower or 6x slower compared to the SR-IOV cluster that we had. And on Comet, now with SR-IOV, the slowdown is just 8% compared to the. And I think this will probably be the worst case for this size of applications. Now, one thing that might be very different is if you start scaling this up. I'm not sure what the jitter and all that is going to do to the scalability. But in general, like a lot of people who ask for the flexibility in stack haven't been looking for big clusters. They're actually looking for flexibility in an environment at a smaller size. So I think this is really good news in terms of performance. And with MVAPICH2 Word, I think things will only get better. So I want to summarize. Basically, the architecture is geared to support like a huge range of applications and a diverse user base. And with virtualization, we hope to even increase that even more. And given all the architecture details and all the different options we are choosing, I think the whole suite of MVAPICH is going to be on there. So MVAPICH2, MVAPICH2X, GDR, Word, and as I mentioned, the RDMA Hadoop is also there. And just out of the box, we got pretty good performance with a diverse array of applications. Thanks.
So thanks for the great presentation. I was looking at the virtualization numbers, and it strikes me that we are always saying that you can do virtualization with X% overhead and X% comes down or goes up.
Yeah.
But that is not the reason why somebody would want to use virtualization. So are you seeing any benefits from virtualization?
So that's the project. We are at the start of it. I think the demand is there for the cluster level stuff for sure, because we've been asked this question a few times, and especially like like the high energy physics people, they have a really nice stack, which is huge and complicated, and I think Carl can tell you how long it took to port that to Stampede, and all kinds of issues, and you have to work through. It's a lot of man hours to get that working, and those sort of groups are very capable of doing it themselves. Like if you give them low-level access. So the real bottleneck for them was the performance, right? Like if you see a huge hit in performance, then they don't really want to do it. But
so it's the OS porting, or like when you say
no, it's basically their software pieces require certain things to be installed, which will conflict with what we have already installed. And we can't really change that for a whole system to benefit one user. But in this case, we just hand them the raw system, let them do it.
Okay.
And there are a few groups like this. So what I want to clarify is this wasn't meant to be a cloud kind of thing where I think that's
that's a different use case origin. That was what I had in mind. Is you want to interleave different use cases, but here's just the software environment. You want to give them a unified software environment.
Big groups which have like people who can manage a cluster or already manage clusters, they can extend their environment into Comet essentially and get like the physics group I was talking about. They might have a big ramp up in usage for like a few months and then go away. And they are fully capable of managing their stack. And we ran them on Gordon once, but they have to do lots of bells and whistles to get things to work. So this is easier.
So if again, I don't know if there are other questions, but if Carl's dream comes true and you have a unified HPC software stack where people are publishing their configurations and so on. So can someone just take that type of thing, customize that, and then say that, okay, here's my spec file for my app, and every time you reboot the node, you boot it with a spec file.
Yeah.
In fact, if I can add, I think of like a Limit module when we introduced. Not many people were ready, am I right? because needs a change. But if it's a virtualized environment, any user can just trigger it and use it. So I think that will, if HPC and virtualization come together, you will see it will a lot of these kind of things will get flourished. Like a lot of people will try to introduce newer stuff which can run on existing clusters like Comet and all. Also the Chameleon cloud, people can experiment, and then once it becomes mainstream, then it can be used by others.
So about the software stack, I think I should say we are putting everything on GitHub. So we manage all our software through ROX, and even this virtualization would come through ROX. And actually, all our roles are public; they're on GitHub, so someone can potentially take that and build it right now and do that.
And one quick question, Mahidhar. Some of the results you compared against an EC2 instance that were pretty drastically different.
Yeah.
Were those their HPC instance, or are they something different? Why
No,
do you think that's
so it's a first thing. It's a 10 gig interconnect.
Oh, it's yeah.
Right. They don't. Do they have?
They have some InfiniBand.
They have some InfiniBand, but I'm not sure whether it's publicly available or
Yeah.
I need to do something.
So this was a 10 gig instance.
I see.
The other is even with SR-IOV, that 10 gig doesn't do too well on Amazon. I think it's, if I remember right, the bandwidth capped out at 500 megabytes per second, which is why.
So those really were receiving influence of networking your results there.
Yeah.
Thanks.
Any questions? Yes.
I see the numbers looks very good. One question is how many VMs per node you have? You typically?
So typically, we the whole node is one VM essentially.
Oh, okay.
So we are not. So I think there are two different use cases. There's a cloud kind of thing, and I think Chameleon is probably a better platform for that kind of work, where you want lots of VMs and want to try out the whole thing. For us, it was mainly focused at give the whole node to the user so that they can set up their environment. That was without losing performance on the IV side, essentially.
Okay, and another question is compare, for example, I see you have in main numbers or Comet, right? The overhead becomes very minimal. I mean,
Yeah.
What's the particular reason why Comet is so good?
Well, lots of things. So when we first did the first set of tests, that was very early days for SR-IOV. There was a lot of jitter on the node. We could actually see things going, even latency numbers were very different at that time. So I think things have just improved. We didn't do much. It's like by the time the machine was proposed and got approved, I think the stacks improved to the point that that's become almost automatic. And I think, that's, the network is also a little bit better, I think. That's all.
Okay, thanks.
It's FDR versus QDR.
Any other questions? Yeah.
My question is, I remember, I believe the virtual cluster on Comet is will be available soon, right?
It's coming, yeah. What we've done is we've tested the process, but there's the other side to it where a user should be able to come in and request something and have that whole process happen without them having to do lots of things. And that's what we're working on now. So it's a few months, it should be available.
Okay.
It's in process right now. So I mean, production date is supposed to be around December, but I think we'll get early users on in the next month or two, very, very quickly.
Okay. Actually, my question is, for the end user, how the user can submit the jobs to how they configuration to configure the virtual machine.
So that interface is still under development, but essentially it's going to be managed with ROX, and you would basically submit a job into regular Comet, and on the back end, that's what would happen. And you would essentially get the nodes, and they would get booted up with the ROX setup, so all the network and all that is set up, right? But then it's up to you what you put on it.
So it's not based on the
OpenStack or anything.
OpenStack. Okay, I see. Thank you.
Yes, of course, I got one. So I know the Livermore admin team had considered some virtualization with virtual machines, and one of the things that really freaked them out was the security model. Right? If there was some low-level security patch that needed to be applied to some software.
Yeah, that's going to be a tricky one.
How do you get your users to
glad I'm not in the security group. No, I mean, I think monitoring is all we can do. I mean, we are a little more open than you guys, so that helps. And I think at some level it's monitoring and letting. It's already the case, though, right? I mean, if you look at it, we have a bunch of machines in our colo, which we don't manage. And a lot of people have, I mean, they have root on the machine, they're on the same network. They can do, whatever damage they can do there will be done here, too, essentially. I think from a security point of view, it's a more monitor and see if anything bad is going on and contact the user. And again, there, the fact that we are going to target groups rather than targeting, like, it's not a cloud instance where everyone can just go run. It's more particular research groups, and we have direct contact with the admins of the groups. So I would say the use case is more, 10 to 15 user groups rather than hundreds of users. So it's easier to manage, even talking to people and making sure they're on the same page. Which fits in with, which we already do for the colo systems on our, within our fabric, essentially. So.
Okay, any other questions? Okay. Now I just have one comment. I think you people use all our stack. I think MVAPICH2 mic is missing.
Carl, we need some mic.
Okay, with that note, let's take a break. We'll again come back at 10:45.